Thank you. That's great. And hello to everyone in the room and online. I presume you can hear me. Right. So, yeah, thanks for the invitation to speak to you today. And what I want to do in this hour with you is, take you on a bit of a tour of what we know about galaxy evolution throughout cosmic history, and especially with a focus on insights we've gained using radio continuum surveys. But modern day astronomy is very much a multi-wavelength enterprise. So a lot of what we can deduce from radio surveys really is inferred making use of ancillary data from lots of different observatories. And I hope to be able to highlight those links as well and the importance of that synergy. So yeah, my name is Mark. I've highlighted the names of a few collaborators on this title slide who have been especially important in developing some of the material I'm going to show occasionally coming from my own research, and also several of the collaborations I've been involved in and from which some of these results are drawn as well. And I really like to start my presentation with an invitation to you to join the Extragalactic Radio Continuum community, and specifically what I'd like you to do, if you're so inclined, is to do this with a forward-looking perspective to SKA science in the radio continuum band. And this is just an overview of the different science topics that are being addressed by a science working group I used to chair for several years, from the mid-2010s to a couple of years ago, the Extragalactic Continuum Science Working Group of the SKA Observatory. So we are already now well over 100 scientists and harking from many different countries, looking at a very broad range of different science topics, which you can see here. So yeah, I'd just like to invite you, if this is of the slightest interest to you, to not hesitate to sign up for this science working group. The sign-up process is very easy. You just have to contact the current science working group chairs, Catherine and Fatime, and they will arrange for you to be put on the mailing list, and you can then start following the scientific discussions, which vary in intensity depending on the stage and what needs to be done. But yeah, for sure, this is a very good way to keep in touch with all these questions. And here in the lower right corner, just as a very brief introduction, I'm showing the relevant part of the radio spectral energy distribution. So you see the continuum spectral energy distribution with the intensity, the total intensity with the solid line here, consists of different components, which we'll touch on occasionally in my presentation. But yeah, the really dominant one is synchrotron emission, the dominant one in terms of intensity. And it is complemented towards higher frequencies by an emission component from free emission and ramping into the far infrared, the spinning dust or the thermal dust as well. So yeah, most of what I'll be speaking about today is on the radio synchrotron emission, with a sprinkling of free from time to time. And the topics I hope to cover really have to do with this cosmic mass assembly over time. I want to say a bit about the status quo, what we know already in broad brush terms, but also highlight some open questions. And it's going to be really important to me to give you some highlights from current extragalactic radio surveys as well, so you get a bit of a feeling for how what is being discovered right now relates to sort of this big picture we have formed over the past couple of decades. And in doing so, I also wish to illustrate a bit of how future SKA surveys enable new territory to be explored. And in this talk, being fully conscious of the fact that you've probably mostly heard about fairly low frequency observations, I do want to make it a bit of a promotion exercise for observing with SKA mid as well, because SKA mid, the telescope observing from roughly 400 megahertz to higher frequencies, maybe all the way to 15 or even higher frequencies in the future, has a unique ability in probing very deep into the faint radio sky, and in a very pinpointed way as well, with high angular resolution observations to really distinguish radio emitting processes on a galaxy by galaxy basis and even within galaxies for subregions within galaxies. So yeah, that's the outline of my talk. If you have pressing questions during the talk I will be giving, you can interrupt me, don't hesitate. I'm happy to address them right there on a given slide, or otherwise I'll leave, of course, some time at the end for you to ask questions on anything that was unclear. So yeah, this is a galaxy in the cosmic web, a cartoon of a galaxy, of course. This is a drawing. And I just want to use this cartoon to highlight some of the different things we can learn with respect to galaxy evolution from observations in the radio. So, for instance, right, not only focusing on continuum, although that's what I want to speak about most, H1 emission, you're very familiar with that emission process, can be traced to the star-forming disks themselves, but also, the accreting material flowing down from the intergalactic medium by gravitational attraction onto the baryonic core of galaxies at the center of dark matter halos. So yeah, 21 centimeter spectroscopy, but also, especially for high redshift galaxies, for SKA mid, molecular lines as well, if they are redshifted down into a few tens of gigahertz range. So these are submillimeter molecular line transitions. And again, the dense gas that forms stars is located more towards the center, really, of the baryonic concentration that galaxies have at the center of their dark matter halos. At similar sites, the dense gas gets converted to stars. The star formation process itself can be traced by radio continuum emission in this case, and both the thermal free component and the non-thermal synchrotron component. If you look at the continuum but limit yourselves to polarized emission components, then you have information on magnetic fields in disks. So again, another important component in the energetics of galaxies. And especially if you have very high angular resolution observations, looking at the very center of galaxies, but also all the way out for giant radio galaxies, for instance, you can follow AGN activity through the non-thermal continuum mostly. And this really goes from the core emission close to the central supermassive black hole all the way out to kiloparsec scale, sometimes even megaparsec scale outflows. So jets on various scales, basically. And especially for interacting galaxies, often the region between those interacting galaxies or between interacting structures in general, there will be such an example as well for connections between clusters later on in my talk. That region between objects, between galaxies or over densities, those are not empty. They contain, for instance, magnetic fields, which can, again, be traced with such synchrotron emission. So really, a multitude of things you can learn from radio galaxy surveys. A more exotic example would potentially, probably not for high redshift galaxies, but nearby objects, even be certain lessons to do with particle physics questions as well. But this is not something I will talk about in my presentation. So yeah, I want to tell you a bit about what we know about cosmic mass assembly, so the buildup of galaxies. And a very important diagram summarizing this, which you've seen probably in many talks already, is the star formation rate density plot, the cosmic star formation history, as it's also called. So here, as a function of look-back time, and that's the upper axis, so the early universe is on the very right. This is from a review paper of roughly 10 years ago, and of course, this is very much a topic of current work as well. You see on the y-axis, basically, the amount of volume average star formation rate taking place in a co-moving volume of the same size as a function of cosmic time. And you see, right, that this peak here is located at redshift 2, or a look-back time of roughly 10 gigayears. And this is what we call, the peak of cosmic star formation history, or the also cosmic noon. And around this peak epoch, you see that things weren't always that active. The cosmic star formation rate density ramped up from the early universe to that peak epoch, and since then has been coming down consistently. And of course, what this just expresses here, this star formation rate density, is a buildup of mass in stars in galaxies. And this is what I'm showing on the right. So the very early universe is on the top right here. So you see the number of galaxies with a given stellar mass. This is the stellar mass function, so-called, of galaxies. The darkest colors are the highest redshifts. And you can see, going from redshift 8 to 4 in the upper diagram, how more and more galaxies of a given mass get added. So the amplitude at a given stellar mass on the x-axis just increases with time. And this continues, and this would then be the lower figure, but it's maybe almost easier to see for reference up to the present day. The gray curve here for reference is the redshift 0 stellar mass distribution. And so if stars are formed, right, then you measure the cosmic star formation rate density evolution, which is shown on the left. So how come? How can stars be formed in this abundance throughout cosmic time? Well, there has been a lot of work done on this over the past 15 years or so, and I've tried to summarize it on this slide. So looking at the upper left corner, which is work I was involved in specifically, but there are many other examples in the literature, you see in this panel A on the very top left, the ratio between gas mass and stellar mass in galaxies as a function of look-back time going from left to right. And you see how the gas fraction, as this is called, increases very strongly with cosmic, looking back to the early universe, or comes down as you go to the present day. And this is reminiscent, right, of this decrease here of lower cosmic star formation rate density with increasing time. Conversely, if you look at the second panel here, labeled B, you see the evolution of a quantity that is often called the star formation efficiency, or sometimes also expressed as the depletion time. So the only thing I want you to take away here is the difference, basically, in the dynamic range between the gas fraction evolution and the star formation efficiency evolution here. And you can see that right, the evolution in this depletion time quantity, or this is just 1 over the efficiency, is far less than the gas fraction evolution. And this would be the same if you look at some of these other incarnations of this measurement in the other figures. You see the interstellar medium or gas fraction content varying more than the star formation efficiency evolution, also in this figure in the lower right, for instance. And what this means is that basically the cosmic star formation history is a history of the availability of in situ gas within galaxies that can be converted from gas to stars. And this could proceed for each individual galaxy in a very disorderly fashion, right? In bursts of star formation occasionally, once here, once there in the cosmic web, very disorganized, or it might not. And so this slide here shows what we have come to call as the main sequence of star-forming galaxies in the literature. And there is a lot of work that has gone into this, but fundamentally what this relation is a correlation between the current star formation rate, that's the y-axis on all these panels, and the integral of the past star formation rate, which is the stellar mass. So to form stellar mass, right, the amount you have present in the galaxy right now is the result of all the star formation that has taken place in the past. And so the star forming main sequence is a correlation between these two quantities that is seen very well at low redshift. This is the left-hand panel, but also at increasingly higher redshift. In this case, I'm just showing a summary from Whittaker et al. going up to beyond the peak of cosmic star formation history, but this relation would extend to even higher redshifts, and I'll show you some of that data in a bit as well. And what this means, getting back to the statement I made when I started showing this slide, is that you don't see objects actually scattered with wildly different star formation rates at a given redshift throughout this parameter space. There is a correlation. So what this implies, especially if you think of the two quantities here on the x and y axis, is that you can essentially write down a differential equation for the growth of galaxies. So the y-axis quantity, star formation rate, or dm dt, right, with the stellar mass being the quantity that is changing, is proportional. Typically, this is an approximation to the stellar mass to the power 0.8. And if you solve this differential equation, although you must do so realizing that, of course, individual galaxies will fluctuate a bit around this trend, but this does potentially convey a picture, right, where different types of galaxies show some similarity in the general evolutionary path they have taken. And I wouldn't want to be quoted on this in more than this very general way of phrasing it, but it does suggest some commonality of evolutionary pathways for lots of galaxies. And that commonality implies that if you solve this differential equation with different initial conditions, different starting masses, for instance, and this is the plot that is shown in the lower right corner, that if you have a high mass initial seed, okay, so red here, for instance, an early seed at very high redshift of 10 to the 10 solar masses, due to the slightly nonlinear slope here, the 0.8, rather than just a slope of 1, galaxies that were already high mass early on, their star formation rate starts to fall earlier than low mass galaxies. So this is, for instance, the contrast between the dark curve here in black and the red curve, right? As the high mass galaxies are already reducing their star formation, the lower mass galaxies are still increasing their star formation. So yeah, that's interesting. Not total disorganized galaxy star formation histories, but a certain commonality of evolutionary pathways. And we can try to link this a bit more also to the general cosmic scaffolding in which they reside. So an interesting result, which again is measured in various ways, is this plot of stellar mass on the y-axis over the total baryon mass, basically, that is available to be incorporated in galaxies as a function of the halo mass. So on the x-axis, this is the dark matter halo mass. So yeah, low mass galaxies on the left, high mass galaxies on the right. And you see this very triangular shaped distribution in all these panels, and the different panels are just for different redshifts. The more you go to higher redshift, the harder it is to probe the highest masses, because these high masses have not been established yet. And of course, there are also observational sampling issues here or challenges at play as well. But let's just focus at the redshift 0.1 panel. And what you see here is that the halo scale at which it was most effective, or the galaxy formation process was most effective at incorporating baryons into stars, is where this peak is located at 10 to the 12 solar masses. And you can see that even here, only roughly 10%, 20% of the baryons were incorporated into stars. But what I really want to highlight here is that this sweet spot for baryon conversion into stars lies at a pretty similar halo mass across most redshifts. And it is at this characteristic scale of 10 to the 12, roughly. And this is an interesting scale also for us, right? Because our Milky Way, for instance, being a galaxy of a few 10 to the 10 solar masses, lies in a 10 to the 12 solar mass dark matter halo. So we, in some sense, seem to be an example of a galaxy at the sweet spot of this evolutionary process. And if you now combine this insight about the sweet spot for baryon incorporation into galaxies and conversion to stars, and this has to do with feedback processes from AGN at high masses and star formation, expulsion of gas at lower masses. If you combine this information with the evolution of the dark matter halo mass distributions, then we can understand something more about the cosmic star formation history as well. So what I'm doing here is just giving a very broad brush combination of two observations, or rather theoretical understanding and observation. So on the left-hand side, the figure we've just discussed, and on the right, you see the evolution of the dark matter halo mass function as simulated by Joe Short and collaborators with time. So the highest redshifts are the purple colors here, moving through green, yellowish around redshift 2 to redshift 0 with the red curve. Or put differently, if we don't look at number of halos of a given mass, but sort of the mass density, so n times m contributed by the different halo masses, then you see that actually the peak of the cosmic star formation rate density coincides to the epoch at redshift 2, so that's this yellow curve here, where the sweet spot at 10 to the 12 solar masses of this baryon incorporation ability corresponds to the knee of the mass density distribution here. So yeah, this is how we can understand the peak epoch of the cosmic star formation history, in that it is where galaxies with the right halo mass were most efficient at incorporating baryons right then. And of course, the supply of gas is plentiful, as I want to show you on the next slides. So yeah, as I told you, right, the cosmic star formation history essentially is a history of the availability of gas in galaxies. And gas comes in different phases. It resides in different places around and inside galaxies. And so this study done with the ALMA Observatory by the Aspects collaboration a couple of years ago really tried to quantify all this in a broad brush way, using basically flow equations, mass flow in and out of galaxies between different components within galaxies. So what I'm showing you on the very left here, the left-hand half of the slide, in part are graphs you already are familiar with. So for instance, the cosmic star formation history had a shape, a bell curved shape, very similar to the blue graph here. But the blue graph here is the cosmic mass density in molecular gas. So the star-forming gas, basically, the dense gas that can be converted to stars. And so, yeah, this unsurprisingly has the same shape. The overall mass density of the universe is the black curve here, the mass in gas, I should say, in galaxies, I beg your pardon, the overall mass in galaxies. And it is composed of different components, of course. So there's the molecular gas, which I showed you in blue, and there's the result of the star formation process enabled by a molecular gas reservoir or other diffuser gas phases. So the mass in stars, the stellar density in galaxies, which dominates very much at the present day, is the red curve. And you can see how this has just, of course, increased over time as a result of the star formation process. And so, yeah, what the Aspects collaboration, and in this Walter et al. Paper specifically did, was to write down simple flow equations. So a loss of molecular gas or an increase, there are different contributions here, which might cause this to be negative or positive, depending on the context. And the same flow rate equation, an evolution equation, sorry, for the H1 component, the atomic gas in galaxies. So molecular gas and atomic gas, and contributions which cause to increase the molecular or atomic component, and contributions which cause it to decrease. And what you find if you set up these flow equations and relate them to the overall net change measured here on the left-hand side, right? So we know these quantities here, d rho h2 dt, d rho h1 dt. They follow from the graphs over here. Then we can infer information about how gas moves from outside galaxies into galaxies and inside galaxies between different components. And the bottom line I simply want to leave with you with here, without going into much detail, is that if you look at what happens with the H2 and the H1 components, so the orange and the blue curves here, you see that changes in these components, and specifically these are losses, right? So loss from H2 to building up stars, loss from the H1 phase, moving gas from the H1 phase to generate stars, or losing it to the outside world, gas being expelled from galaxies. Those losses are small compared to the gain that the stellar mass has had over cosmic time. And what this means is if there is such a large discrepancy, right, there needs to be, and this is the bottom line I want to make with these two slides, there needs to be a lot of accretion of gas from the intergalactic medium onto galaxies. So recall one of my very first slides, these streams of gas flowing onto the center of dark matter halos and the gaseous disk there. This is quantified, the net effect of such streams. But there is very much an open question here, which current radio observatories and next generation radio observatories will address. And this is, the different gas phases these streams can augment. Ionized gas, diffuse atomic gas, dense molecular gas, cold molecular gas. There are lots of different phases. And this is something we actually know very little about. So we have some information in a very statistical sense from the study I just showed you and others of the relative abundance of molecular dense gas and more diffuse atomic gas. And this is the figure here shown as an inlay. And you see that, well, maybe around the peak epoch of star formation history, these two gas phases reach a roughly similar abundance. But as is shown here by this image of a H1 distribution in M51, a nearby galaxy, the H1 in galaxies, the atomic phase, extends very far beyond the stellar body of galaxies. So there is lots we will learn about these more diffuse gas reservoirs outside galaxies. And yeah, just to highlight how much we will learn, the farthest away detection of a H1 reservoir in a galaxy is actually only at redshift 0.4. So yeah, there's lots of progress we will make over the next decade or so, and progress is being made as we speak. And I especially want to highlight the contribution of the upgraded GMRT in this, where Choudhury et al. Have really used the information from spectroscopy in the deep 2 fields to push the limits of our understanding in this respect. So they have not detected individual galaxies in H1, but they have used the spectra from lots of optically detected galaxies, and they have measured through line stacking the average gas content of star-forming galaxies around redshift 1. And what you see here is this beautiful detection on the left. This is a stacked H1 line emission signal, and in the image plane shown here on the right of galaxies at redshift 1. And what this suggests is that the ratio between H1 content and stellar content at roughly redshift 1 is such that there may be more H1 associated with such galaxies than stars. So yeah, this is tantalizing evidence of a baryon budget in high redshift galaxies, which we'll learn much more about in the coming years. So I'm going to skip over that slide and move a bit more to another very important question in galaxy formation and evolution. And this is the relation between the growing stellar content of galaxies and factors inhibiting that growth. So specifically, different feedback mechanisms. And the supermassive black hole at the center of galaxies is often held to be the culprit of such inhibiting factors. So one of the key questions we often ask in this context is so-called galaxy supermassive black hole coevolution the result of just, you're sitting in the same gravitational potential. That gravitational potential attracts gas, and both the black hole growth and the feedback the black hole can then exert on the galaxy, and the growth of the galaxy itself in stellar component, they can tap into that same gas reservoir to grow. Or, is there something more active going on in feedback? And the reason why we speak of coevolution is highlighted in these two figures. So the left one you know very well, that's the cosmic star formation history, the same bell curve I've showed you a couple of times already. And the right-hand side is a curve which has a very similar shape. And I just want you to highlight, to look at basically the colored, the two colored curves here in red and green. So these are measures of the black hole accretion rate density as a function of time. And you see, these have a very similar shape. They peak at redshift 2 at the same epoch as the cosmic star formation history peak. So this is one piece of evidence for galaxy supermassive black hole coevolution. And it suggests that when galaxies grow most strongly, when the growth rate is highest, the growth rate of their embedded supermassive black hole is highest as well. So how come? And this is very much a topic of current research. In the lower left corner, I'm showing you a so-called AGN main sequence, a radio AGN main sequence in recent work by Del Vecchio et al., where, thinking back to the star-forming main sequence I spoke about several slides ago, you see again a general correlation as a function of stellar mass of, in this case, the AGN luminosity at gigahertz frequencies in the radio, showing an increasing dependence in the same way as the star formation rate increased with stellar mass if you looked at the star-forming main sequence. So these are even the same galaxies. These are actually star-forming galaxies which have an embedded AGN that shows the same dependence on stellar mass, roughly speaking. Not exactly. You see here there's a different slope. It's not 0.8, it's 1.4. But again, there's broad brush qualitatively an increasing importance of AGN growth, of black hole growth as a function of stellar mass. So this is the scenario where they basically are able to make use of the same gas supply in somewhat similar ways to grow stars and to grow their supermassive black holes. But of course, there's also lots of work being done and finding evidence on a more case-by-case basis that really the AGN feedback process and the triggering of AGN happens in very specific phases of galaxy evolution. So, reconciling these two pictures, these two paradigms, is an area where we still have a lot of work to do. And we also still have a lot of work to do, and I will skip all over this very quickly. We have a lot of work to do to understand where within the cosmic web supermassive black hole growth and galaxy growth takes place in the most efficient ways. And I've just included this slide without wanting to go into details to tell you that at the moment, using available studies, the statement on, say, the shape of the main sequence and how it changes as a function of environment from dense environments to diffuse environments, so for instance from clusters to voids, that the view of this, depending on the kind of measurement you make and the kind of data set you make, varies very substantially. So again, big open questions. How does galaxy evolution depend on environment? Very much an area of current research. And just to close this whirlwind tour of what we've learned about galaxy black hole coevolution, but also galaxy growth, I want to show you this slide. So I've talked a lot about general galaxy properties, volume average galaxy properties, but inside of galaxies, there of course are various constituents that grow and change shape over time. So for instance, when does the disk grow? When is the bulge formed? How is material exchanged between these two components? Does the changing morphological composition of galaxy or the differential growth of different components in any way relate to this evolution of the star formation efficiency, this mild evolution which we've seen? And here it's interesting to just consider anecdotal evidence, for instance, from a galaxy, in this case at redshift 1.5 in the upper right corner, where I'm showing you a snapshot, a stamp of this very heterogeneous galaxy. You see it's quite clumpy. It clearly has regions forming more stars than others. So this is all one galaxy I'm circling here. I hope you can see my cursor. You see clumps of star formation of different colors. And on the right-hand side, slightly in the background, I'm showing you two curves, a blue one and a red one. And what this is what we call a spectral line excitation diagram. So the J values here are quantum numbers for transitions, rotational transitions in the CO molecule. And the only thing I want to do is highlight that if you look at different parts of this galaxy, and this is an emblematic galaxy for such galaxies around cosmic noon, you see that depending on the region you look at, so either the blue half or the red half, the excitation of the gas actually is different. So the blue region with these clumps here, you see that in this higher order excited state, it is much more excited than the red region. So this tells us something about the underlying conditions in the interstellar medium, where apparently, often, this is a result we find, and that is exemplified in the lower right corner, excitation, for instance, correlates with star formation efficiency. So the conclusion would be that here this galaxy is forming more efficiently its next generation of stars in the upper right corner than in the lower left corner. So yeah, why is that? How can we understand this? And this is where I now want to get into the future role of radio observations with SKA mid. And really, there's a whole range of reasons why you'd want to use a telescope like SKA mid. It has high angular resolution, meaning you don't blend sources of emission. It has high sensitivity, meaning that once you've, thanks to the high angular resolution, zoomed in on exactly the region you want, be it an individual galaxy or even a region within the galaxy, you actually have enough collecting power in the telescope, enough collecting area to be able to detect quite faint emission and quite faint processes. Doing galaxy surveys with SKA1 mid is very much commensal in that you can use the same data stream to do continuum science. You can do spectroscopy as well, so you can generate from the initial data cubes 2D images for continuum. So you can do H1 science, you can do continuum science. And a strong advantage in all of this of radio emission is that it is dust unbiased. So thanks to the long wavelength, you can basically look through dusty regions and really follow growth processes even in the most obscured parts of galaxies. And you can do so, as I said, right, at a very high angular resolution. And this slide is just to show that and put it in context. So these different wedges here, as a function of frequency on the x-axis or wavelength, show you the angular resolution that different observatories reach. And SKA1 here, this purple wedge coming down from the top left corner, shows you that right around a few gigahertz, we clearly reach sub-arc second resolutions, angular resolutions that are somewhat commensurate with, say, JWST or Hubble Space Telescope. And of course, if we were to be able to do SKA VLBI, the angular resolution would be even so much better still. But yeah, really comparable angular scales we can resolve to the most highly resolving ground-based telescopes in the optical, or even in some cases, space-based telescopes. And the sensitivity aspect, I can show here with this diagram on the right. This is the parameter space in which both historical radio surveys and current radio surveys live. So this is survey area on the x-axis and sensitivity on the y-axis, on the x-axis. I may have said that incorrectly. So area, y-axis, sensitivity, x-axis. And just looking at constant area, so fixing a position here on the y-axis, what you would see here if you squint is that the planned SKA mid surveys for galaxy evolution science at fixed area, they basically probe roughly a factor 10 deeper than the most sensitive current day Pathfinder or precursor surveys, for instance. So really an order of magnitude increase in survey sensitivity. And they do so at, we expect, a substantially higher angular resolution as well than some of the current Pathfinder and precursor surveys. This relies on the full SKA1 baseline design being implemented, but yeah, that is what we should hope for. And our expectations for the kind of survey work that would be carried out with the SKA are shown here. So yeah, the Extragalactic Continuum Science Working Group, which I mentioned in opening, has defined what it thinks would be a set of tiered surveys, probing both wide areas and in a somewhat shallower coverage and small areas very deeply, the wedding cake approach, as it's often called. We have defined these to be able to do galaxy evolution science with the SKA in a multi-wavelength context. So specifically, band 2, this is 1.4 gigahertz. We'd aim to reach well under arcsecond resolution. And yeah, we have, wide area survey components of order 1,000 square degrees with pointing times on source and mosaicing this over this 1,000 square degree area of roughly 5 hours to just individual very deep pointings reaching an area of roughly 1 square degree. And yeah, where we'd expect to integrate, observe the same part of the sky again and again and again until we reach of order 1,000 hours of total observing time. And we complement this as this survey, multi-tiered survey here on the left for the synchrotron component, as this addresses non-thermal emission, so AGN and galaxy evolution using synchrotron emission. We'd like to complement this with a survey at higher frequencies with 2 tiers, looking at the thermal processes in AGN and galaxy evolution. So this will be targeting the free emission, or at least a part of the spectrum where free and synchrotron are more easily discernible. And here again, we'd be looking at significantly smaller fields, comparable in size to the deepest fields of the synchrotron-based survey, with an aim really also to calibrate the information we get from these 2 different emission mechanisms, free and synchrotron. And just to give you a feeling for the kind of galaxy that we can detect with such surveys, this now focuses very much on the wider, I should say that the larger area surveys on the left here. So my number 1, the tiered survey shown in red for the 1.4 gigahertz coverage. I want to give you a bit of a flavor for the kind of galaxy we can detect with such a survey. So let's just go to the very optimistic deep coverage. So where we will pinpoint galaxies in the most distant parts of the universe with the highest sensitivity. And look at the lower right corner. So the deepest tiers here, the ultra deep tier, the solid lines, we expect them to be able to detect galaxies out to redshift 4 or even higher with roughly 10 to the 9 solar masses. This could be just, of order 1 times 10 to the 9, or for slightly more pessimistic cases, several times 10 to the 9. So this is the mass, for instance, of a Milky Way companion like M33, for instance. So galaxies in the local group have that mass, some of the less massive galaxies. And in terms of star formation rate, again, in the deepest survey tiers, solid lines here at the very bottom, we could detect galaxies with roughly the star formation rate of the Milky Way in its present day, so a few times a solar mass per year, out to redshift 4 as well. So this is the kind of galaxy we will detect thanks to such surveys. And what we will also be uniquely positioned to do with such surveys is to characterize these galaxies in much more detail than we've been able to do so far in the radio band. This is because of the high angular resolution of the future SKA. And of course, we already have examples of such high-resolution surveys coming from, for instance, the E-Merlin telescope and the eMERGE survey in particular, or also at lower frequencies with LOFAR, the LOT survey, especially with international baselines. So what I'm showing you here on the right is, again, for this 1.4 gigahertz band 2 survey, simulated images of what galaxies would look like in a future radio survey. And you see here, right, a galaxy, for instance, at redshift 0.1, clearly discernible in all the details of its spiral structure in the ultra-deep imaging, and already to some extent in deep imaging. And this relates to the tiers I'm showing on the left. And this really places us in a position to characterize the size of galaxies, to make statements about how concentrated the radio emission is. And these are examples shown on the right, where we've looked at the recoverability of such structural information in the radio band in a study that Rose led, and really also trying to apply for the first time optical metrics of size and structure to radio surveys. Obviously, the optical community, the near-infrared community, has plenty of experience based on Hubble imaging, JWST imaging, of making structural measurements on galaxies. And we are now entering the era where radio surveys will be able to do this as well. So yeah, the degree to which a recoverability is guaranteed, of course, depends on the kind of structural information you're aiming to recover. But you can see here, this upper plot, for instance, suggests that for size measures, we will be able to do that quite well. And this then gives us information about how galaxies grow internally, right? That's something I alluded to being an open question a few slides ago. Okay, so in summarizing this optimistic view to what we will be able to accomplish with SKA, I just wanted to leave you with one final message. And this is how commensal these different SKA observing runs will be. And by that, I mean fit for many different purposes. So focusing on the right-hand side, because that is most important to me, that I can convey that information. The SKA has this unique ability to be very sensitive at lots of different spatial scales. The figure in the lower right is a noise measure on the y-axis as a function of the angular scale on which that noise is measured, or on which the sensitivity has been derived. And what you can see here for SKA1 mid, okay, so for a band 2 observation at 1.4 gigahertz, you see that a low noise plateau is reached here around 0.6 arc seconds all the way to almost 100 arc seconds. And this is just a measure of the beam size of the telescope, or the point spread function, as it might also be called. And you can see that this large plateau over several orders of magnitude, this wide plateau, is much wider than is reached, for instance, by the VLA in its individual configurations. And what this means is that, you know, at the same time, for instance, in band 2, you can decompose individual galaxies from the diffuse emission of clusters in which they reside, or at a higher frequency, regions within galaxies in star-forming clumps from the overall emission contributed by that galaxy. So really lots of different spatial scales on which we can create an inventory of the emission seen in radio images. So ending on a few highlights, I just want to give you a feeling for the excitement we can already have from what we're learning with radio surveys that are ongoing right now. And I'm going to end with this. So this all comes from the surveys which are either to the right of this dashed line in this figure we've looked at before, or sort of reside along this second dashed line here. So luminosity function evolution. Radioluminosity function evolution is the first step to understanding how star formation activity as traced by radio emission evolves, or also radio AGN activity. So for instance, right, if you're able to decompose, as has been done here on the left-hand side, the overall radioluminosity function in blue into components from star-forming galaxies and AGN galaxies, and this is what is being done in the luminosity function figures on the left. Then you can reconstruct the cosmic star formation history, peaking at redshift 2, also with radio measurements in the same way as the other measurements we saw. Or using just the AGN component, you can look at energy production for radio mode feedback and how that evolves over cosmic time. This is a result from the cosmos field using JVLA Cosmos data. You can very much use these decompositions to look at the faint radio population. We will probe even in more detail with the SKA going forward. Radio quiet AGN, radio silent AGN even, and how they relate to the star forming population, and the balance between star formation activity and AGN activity in galaxies. So these are population models looking at basically the counts of galaxies of different types as a function of observed radio flux. So with the SKA, going to the left-hand side of these figures at faint fluxes, we will learn ever more about this mix in the faint population of star formation processes and black hole growth related processes. Here is an example of emission, diffuse emission in galaxy clusters. So these are galaxy clusters observed with MeerKAT. They have been selected through Sunyaev-Zeldovich emission. And for the first time, using this survey from Kendra Knowles et al., we detect in such clusters distinct types of diffuse emission. So this is radio emission coming from in between the galaxies and clusters. Radio relics, radio halos, all clusters with signatures of being dynamically disturbed. And for the first time, we see evidence of the processes underpinning these disturbances in the radio. I've talked a lot about the main sequence of galaxies and star-forming galaxies, so I don't want to say too much about this. But again, just to drive this point home, radio emission is dust-free. It is unbiased by dust. And of course, star formation often generates dust and takes place in dense, dusty, gaseous regions. So really, radio emission has allowed us to track this so-called main sequence of star formation, which I mentioned at the very beginning of my talk already, across cosmic time in a very detailed way, across quite a broad range of stellar masses. Okay, I want to leave you with two more examples, and I will.
10 minutes left, Mark.
Yeah. No, I'm wrapping up. So new discoveries that have been made with precursors. And this is an example of magnetic fields in the cosmic web. So here, Tessa Wernstrom and collaborators use data across several different frequencies, mostly working with low frequency data from the Murchison Wide Field Array, the MWA in Australia. And what she looked for with her team was whether there could be evidence of magnetic fields in the cosmic web. So I'm showing you in the left-hand column here, or the central column with the actual astronomical data. I'm showing you combinations, basically, of two related galaxy clusters or galaxy overdensities in the continuum emission. So you see the two bright dots here in the top panel. This is the joint emission coming from two nearby galaxy clusters that are structurally related. They are part of the same region in the cosmic web in that they are located at a similar redshift. And you can model this cluster-based emission. And this is what has been done in the second panel. You subtract the modeled emission coming from the overdensities, and you're left with what is shown here on the third row. Emission in between the clusters, synchrotron emission, which is originating from in between the clusters, and the presence of synchrotron emission implies the presence of magnetic fields. Okay, so this is a detection, basically, of the magnetic structure of the cosmic web. And yeah, Wernstrom and collaborators have looked at this also in polarized emission. This is shown on the right here in panels B and D. And this polarized emission then gives you additional information on how these magnetic fields might be generated. So this is really a pioneering measurement of magnetic fields in the cosmic web. And the presence of structures we were not aware of until very recently is also exemplified by this kind of information from the Meerkat telescope, looking at big radiolobes, giant radio galaxies, and the fine-grained structure of the radio emission associated over large scales with such radiolobes. So specifically, the discovery I want to highlight here is these very collimated synchrotron threads connecting over large different distances the two outflow lobes. And you can see also even within lobes, within the termination point of lobes, very detailed ribbons and rings like shown here in the zoom in for this radio galaxy in the lower right half of the slide. So these detailed structures, their extent, the fact that they exist, the implications for the propagation of charged particles in such outflows is something we're learning about as we speak. Variability of radio galaxies is stronger than we expected. This was seen both at gigahertz frequencies, an example here from Kate Nyland and collaborators, looking at L-band variability over a roughly 20-year timescale, mid-90s to 2020. You see the change in amplitude, the substantial change in amplitude of radio sources. And as shown by Ross et al., again using lower frequency data, even the change of spectral shape of some galaxies of this kind, going from steep spectrum to peak megahertz peaker sources, for instance. So not only a change of amplitude, but also a change of spectral shape, basically giving information on the life cycles, the duty cycle for radio AGN activity. Okay, so I'm done. I spoke a lot about synergies. I could give you lots of examples about how synergies in detail for specific objects like a nearby galaxy here will play out using optical X-ray radio telescopes, basically to do with measuring where objects are, measuring the flow of material around them. And the good news I want to leave with on my final slide here is that SKA entering the era of being a telescope to be reckoned with is really quite close by. This shows the predicted evolution during the build-up phase of SKA as a function of time. So the measure on the y-axis is a measure of sensitivity of the overall telescope. And the thing I just want you to absorb in this figure is that the horizontal lines on the top for SKA mid and on the bottom for SKA low, the horizontal lines designate the sensitivity of present-day radio telescopes. And the crossover point between the growing sensitivity of the SKA observatory, the top and bottom, the crossover point between the solid lines and the dashed lines tell you when SKA will become more sensitivity, that's just sensitive, that's just in terms of collecting area, of course, than the existing observatories is somewhere around the start of 2027, or potentially even a bit earlier for some SKA low observations. So it's not that far away. So yeah, I hope I have convinced you that we can use this already now and in the future even more so, this new capability for radio continuum science in the extragalactic domain to learn lots about radio galaxy evolution, about star-forming galaxy evolution. And I'll leave you with this summary and shall be very happy to take questions.
Hi, very nice talk. So I had a basic question. Maybe I missed this in your lecture. So at first glance, one would assume that the peak of AGN activity and the peak of star formation rate shouldn't be at the same redshift, right? Because AGN feedback would result in very hot gas, and it would not, like the cooling of gas wouldn't be that effective to form stars. So what exactly is happening at cosmic noon, and why do we see like a correlation between these two activities?
I need to be brief. You could listen to entire conferences on that question. I think there is obviously a time lag question in all of this, right? And this is what you allude to. What does feedback do to the different gas phases, and when does it do it? How does it do it? But there is this broad brush underlying insight, right, that the supermassive black hole in galaxies grows in a pretty similar way, at a pretty similar rate, tracking the growth of the stars in galaxies. And I think we really need to distinguish here in that the figures I showed you related to the accretion rate of the supermassive black hole, the growth rate of the supermassive black hole. It is not the feedback itself, right? The feedback happens in different ways at different cosmic epochs, the type of feedback that happens. We know that the balance of radiatively efficient or inefficient feedback happens in different ways at different redshifts, in different types of galaxies. So radio mode feedback, just to give you an example, at low redshift is seen to occur most frequently in early type galaxies, elliptical galaxies. But at cosmic noon, radio mode feedback is most prevalent in gas-rich disk-like galaxies. Okay, so things change as a function of redshift. And really, I think, yeah, the important analog to make is the plots I showed you show black hole growth rate, and the point at which that translates to that black hole being able to exert substantial influence over the galaxy is not exactly then necessarily.
Thanks.
Any other questions? If you feel shy, you can post it on Slack as well. That option is always open. So there is a Slack channel. I have added you there, Mark. So you can check if people do post anything.
Yep. And I'll arrange for these slides to be uploaded as well.
Okay, so if there are no further questions, let us thank Mark once again.